So with this lecture we begin chapter 9 on operational amplifiers. Uh, what we'll do is whatever we have learned until now in this course, from chapter 2 till chapter 6, we will put it all together and think about architectures for designing general purpose operational amplifiers. And by the term operational amplifier, we will mean a two input, single output, high gain, high output resistance amplifier. Alright. And by high gain, we will mean a gain of the order of GMRO squared or higher. We'll start with GMRO squared and then go to higher. For us, Rin will be infinite because these are all MOSFET amplifiers with the input supplied to the gate, and so the input resistance is infinite. Note that I have not mentioned output resistance because you recall some lectures ago I had mentioned that MOSFET amplifiers do not typically have low output resistances. So in this chapter, the circuits we look at will not have low output resistances. A similar chapter on bipolar op-amp will have low output resistances, but that is outside the scope of our discussion. Also, op-amps are designed with two inputs and two outputs. So, but in this course, we will not look at circuits with two outputs. We'll make a passing reference once in a while to them, but our focus will be single output amplifier. Inputs will of course be two. So the first question in fact we ask is, why do general purpose op-amps, so you go to any analog circuit vendor company that makes op-amps, you will see that all op-amps have two inputs. You will hardly, in fact, you will not find any op-amp that has a single input. So why is it so important to have two inputs? So you think and maybe write down the reasons why you think it is useful to have two inputs rather than just one input. All right. So please pause and write down and then continue. Okay, here are a few major reasons. One is that differential systems where two inputs are applied and the difference between two signals is taken cancel noise very effectively. And we saw this in fact in very briefly when we looked at the example of an ECG signal. There are a large number of applications where one wants to amplify the difference between two inputs. Another major reason is that all op-amps are used with negative feedback, and negative feedback would require that you take the output, sample it and then subtract it from the input signal. And so in order to facilitate the subtraction from the input signal, two terminals are extremely useful. Of course one can do it with one terminal, but two terminals facilitate the process of subtraction of the feedback signal, particularly for voltage series feedback, which you hopefully have studied in your undergraduate curriculum. And also, of course, a two input op amp is a more general circuit or a chip or whatever. It can always be used as a single input op amp, just ground the other input. So the two input is a more general purpose system compared to a single input, and that is why all op amps are two input op amps. Alright, the next question we ask is, what is the need for such high gain amplifiers? You know, op amps, as I said, you go to the website of Analog Devices or Texas Instruments, you will routinely find op amps have gains of 10 raised to 5, 10 raised to 6. It's common. What is the utility of such high voltage gains? Alright, so let's look at one example to illustrate that. So you may have heard of pipelined analog to digital converters. You probably know or don't know that they are the fastest A to D converters available today for high resolution. At low resolution, flash ADCs are the fastest, but you go above 10 bits or so, then pipelined is the fastest ADC available. In fact, all the audio and video applications, all your smartphones and MP3 players, no, not MP3 players. MP3 players only have a digital to analog, but the smartphones all have a bunch of pipelined ADCs. Okay, so the pipeline is a architecture which has stages, right? It is a pipeline of stages, and each stage of the pipelined ADC requires an amplifier that amplifies the difference between two input signals, and that amplifier needs to have a gain of 2 raised to m, where m is a number of bits resolved by that stage. Most often m is 1, and so this gain needs to be 2. Alright, I'm not explaining, you don't need to understand all that I'm saying here. This is just background. Now the accuracy of the overall A to D converter depends almost entirely on the accuracy of this gain being 2. The gain of this amplifier has to be 2 or very, very close to 2. So for example, for a 12-bit ADC, it can be shown that this gain of this amplifier with a gain of 2 has to be within 2 into 1 plus or minus 1 by 2 raised to 14. For a 12-bit, you read 1 over 2 raised to 14, which turns out to be 1.999878 to 2.000122 or 0.01%. Alright, so it is required for all the pipeline ADCs in the world that an amplifier be available whose gain is within 0.01% of 2. Alright, so now let's think about designing such an amplifier. This whole semester we've been designing amplifiers. So now we want to design an amplifier with a gain of 2, but whose gain does not vary by more than 0.01%. So we say, well, of course this is a differential amplifier, 2 inputs. So we say, well, let us think about the simple differential amplifier with a resistive load. The gain is only 2. So we know that we can get a gain of 2 easily with the simplest possible circuit. So we say, okay, we'll build this circuit, and we know that the gain of this circuit is Gm Rd parallel Ro divided by 2. And then we design the values of Gm and Rd and Ro, all that, to make sure that this is equal to 2. Just the design of this is trivial. I think you can do it in 10 minutes if you sit down and do it, if you are given all the VTs and the mu and C oxes and all that. Alright, but here is the problem. The gain of 2 does not stay constant at 2 for this amplifier. It varies with temperature, process variations, and in fact with the DC voltage levels, because there is a GM here. So if you think of GM as 2ID over VOV, VOV will vary as the input voltage signal varies, and as VOV varies, GM varies, and GM varies, the gain varies. This gain is far from constant, and because of all these variations, the gain can vary as much as by 5 to 10%. And we want a gain that varies by less than 0.01%. 01 or 02? Okay. Now let us look at, so we looked at this. Now let us look at an op-amp. A simple inverting op-amp, 2R, R, and an op-amp. Alright, and if you were to derive V over V in for this op-amp, assuming that the op-amp gain is A0, not infinite but A0, then you can derive, I'm not deriving, but because I think you've done this, you should be able to do this by yourself. So with 2R and R, you will find that the closed loop gain, or just V over V in, of this circuit is 2A0 by A0 plus 3, right, where A0 is the open loop gain of this op-amp. So of course A0 is very large, 10 raised to 5 or so. So you ignore the 3, then the A0 is 0 cancels and you get V over Vin equal to minus 2, which is another amplifier with a gain of 2. Now let us think about this further. So we can write this expression in terms of ACL for A0. So we say A0 is equal to 3 ACL by 2 minus ACL, the closed loop gain which we want to be 2. Now if we want ACL to be 2, of course A0 has to be infinite, which is not possible to achieve. So this gain of course never becomes equal to 2, it is always slightly less than 2. But suppose we say, okay, I'm okay with ACL of 1.9999. Then A0 required is 60,000. Alright. Now we say, if we make an op-amp with A0 equal to 80,000, then you can show easily by just doing some arithmetic here, that even if A varies by 25%, which means if A varies from 80,000 to 60,000 on one side and 100,000 on the other side, which is a 25% variation due to, let us say, process, temperature, whatever, even if A varies by 25%, ACL will change by less than 0.01% of 2. Alright. This can be shown. You just put ACL equal to 80,000, 60,000, 100,000 and find, put A0 equal to 60, 80, 100 in this equation and find ACL. You'll find that the ACL variation is less than 0.01% of 2. This is the beauty and the utility of high gain amplifiers. Even if the high gain of 80,000 varies by 25%, and it will vary because we don't have control over process and temperature so much that we cannot let it not vary. It will vary. But the fact that it is so high makes its effect on the closed loop gain very small. Because as long as, so you look at this equation, as long as A0 stays much greater than 3, then whether it is 60 or 80, ACL is very close to 2. That is why high gain amplifiers are useful in electronic circuits, because they give closed loop gains that are much more independent with respect to process and temperature. Of course, the other advantage which you already know is that I can use this same op-amp circuit or the chip to design an amplifier of gain 2, 5, 10, 100, etc. etc. I don't have to keep redesigning the amplifier each time I need a new gain. I just put 2 resistors, same amplifier, different values of resistors, which is trivial to design. So that is of course the even greater or higher level utility of high gain amplifiers. Alright, I want to digress a little and talk about the virtual ground, which you all have studied in your undergraduate, but I have found that a large number of students really don't know the answer to this question. So the question I am asking is, so let's go back here. When I derived this equation, not this equation, when we find that VO over Vin is minus 2 for this circuit, alright, don't look at these are without making the assumption of virtual ground. But usually what we do is we say, well, op-amp has virtual ground because the positive terminal is at ground, the negative terminal is at zero potential, and therefore if we write a KCL at this negative node, we'll get VO over Vin equal to minus 2 or minus 2R by R, which is minus 2. So we make the assumption that this terminal is at zero potential or virtual ground. The question I want to ask is, can you prove why or how this is at zero potential? Alright, and the answer I most often get from students is that this is 0 because the input resistance of the op-amp is high. Alright, now that is an absolutely incorrect answer. So I want to tell you the correct answer. Okay, so we say for this op-amp, VO is equal to A0 into V plus minus V minus. This is a fundamental property of the op-amp, because that's what the op-amp does. The output is equal to A0 times the difference between the two inputs. So V plus is the voltage at the positive terminal. And in our circuit, of course, V plus is 0. So from this we get V plus minus V minus equal to V0 by A0. A0 is very large, 100,000. Therefore, we say V plus minus V minus is approximately 0. It is V0 by A0. So V0 is, let us say, 10 volts. A0 is 100,000 volts. So that 10 by 100,000 is 0.1 millivolt. We say, well, 0.1 millivolt is small, so approximately 0. Or V plus is equal to V minus. Alright, and therefore if V plus is 0, then V minus is 0, and that is how virtual ground comes. So what is this line of argument? The line of argument is that V plus is equal to V minus is an op-amp because A0 is large. Alright, the fundamental reason why V plus is equal to V minus in an op-amp circuit is because its voltage gain, the open loop voltage gain, is large. It has nothing to do with the input resistance of the op-amp. Okay, I'll come back to the input resistance in a minute. The other thing is, all this is valid, and V plus is equal to V minus is valid only when the circuit has negative feedback. If the circuit does not have negative feedback, or it's an open loop configuration, let's say I remove the 2R, there's nothing connected between the output and the negative input, then of course V plus is not equal to V minus. Alright, the virtual ground or V plus or equal to V minus is valid only in op-amp circuits that have negative feedback and when the open loop voltage gain is large. Okay, please remember this forever and ever. Okay, let's quickly look at the effect of the input resistance. So let's take the same circuit and let us say that the input resistance of the op-amp is not infinite. Alright, here I assumed infinite here and before. Let us say it is not infinite. I am not deriving this, I am asking you to derive it yourself. But if you find an expression for V minus of this circuit with an input resistance that is not infinite and a gain that is not infinite, you will get this expression. Alright, please derive it yourself. It is simple, but it is important to derive. Now let us look at this expression. What is this saying? If Rin is large, then this term is small. So just for the sake of argument, we ignore A0, then we say if Rin is large, the denominator is small. If the denominator is small, this expression is large. So V minus is large. I want V minus to be 0. It's virtual ground. So in fact, a large Rin does not make V minus equal to 0 even by the analysis of the circuit. In fact, it makes it large. The only reason V minus is 0 is because A0 is large. Alright, so this is a more complete expression demonstrating that V minus is 0, of course assuming V plus is 0 as in this circuit. Then what was I saying? V minus is 0 only if A0 is large. Alright, so okay, so that is that. So that was a digression. Let us go back to our, okay, one more thing. Okay, so what I said was, let me go back. What were we saying? We said we want to build for a pipeline ADC an amplifier that has a gain very, very close to 2. And we said this doesn't work. And we said this works, or it seemed like it worked. But the reason this works, the assumption under which this works is that this is exactly 2R and this is exactly R. So that 2R by R is 2. Now it turns out that in integrated circuits, when you fabricate resistances, it is very, very, very difficult to make resistances whose ratio is exactly 2. Alright, so if I make a resistor of 20 kilo ohm and a resistor of 10 kilo ohm, the ratio of 20 by 10, it is highly unlikely that it will be exactly 2. Due to process variations, this ratio is can vary by 1 to 2%. Right, 1 to 2% is not good enough for us. We want 0.01%. Therefore, while designing high precision amplifiers with op-amps, right, a gain of 2 amplifier with an op-amp, one does not use resistors in integrated circuits. One replaces resistors with what are called as switched capacitors, because capacitors have much greater accuracies when they are fabricated on a chip compared to resistors. And the fundamental reason for that is that the resistance value depends on the doping in the silicon, and the doping is much more difficult to control, and that is why resistance values are not precisely controlled. Capacitances depend simply on the geometry. Well, I should say primarily on the geometry, epsilon A by Tox. The thickness of the oxide, the area of the capacitor, these are all geometry, and these are much more precisely controlled compared to the doping, and therefore capacitances are much more accurate, and therefore switched capacitor circuits are used to design and build high precision amplifier circuits. Alright, we will not look at switched capacitor circuits this semester. These are covered in chapter 13 in Razavi's book. This is typically covered in the next course on advanced analog design next semester. Alright, another thing, I want to talk about op-amps versus comparators. I'm not sure if you've heard of comparators. Comparators are circuits which have two inputs and the output is high. If let's say in this circuit, the output is high, V in 1 is greater than V in 2, and the output is low if the input V in 1 is less than V in 2. Alright. Fundamentally, comparators are also high gain amplifiers. Op-amps are also high gain amplifiers. The difference between op-amps and comparators is that by definition, comparators are circuits that are comparators are high gain amplifiers that are used under open loop conditions. One never applies feedback to comparators because the purpose of a comparator is to compare two input voltages and produce an output that is high or low. Op-amps, on the other hand, are almost always used with negative feedback. So this is the fundamental difference between op-amps and comparators. Now, as we'll study in the next chapter, chapter 10 on stability and compensation, negative feedback can cause high gain circuits to become unstable. You probably have heard this before, and you will study this in detail in chapter 10. Therefore, op-amps have to have special frequency compensation done so that they don't become unstable, because they are going to be used with negative feedback. Frequency compensation causes the circuit to be slower. Therefore, op-amps are always slower than comparator circuits. Alright, our purpose in this course is to study op-amps. Op-amps can be used as comparators because they are high gain circuits, only they will be slower than comparators. Comparators cannot be used with negative feedback because if you do, they will just be unstable and instability will set in. Alright. Okay, so our goal to start this chapter, which actually will start in the next lecture, is to start looking at circuits which have two inputs and a gain of the order of GMRO the whole square. Alright, so what I'd like you to do before you watch the next lecture is to list the configurations that we have studied that can be used to build an op-amp of a gain GMRO the whole square. Alright, So of course the first requirement is that it has to be a circuit that has two inputs. So it has to be have a differential amplifier input stage. Given this, can you just list what are the configurations that we could use to build an op-amp of gain GMRO the whole square of the order of, right? This is order. So GMRO squared by 2 is okay, but GMRO is not okay. Alright, so with this I am ending this lecture. Next lecture we'll start looking at op amps of this order.